Dear colleagues in Brazil, welcome to this video presentation. Let me first introduce myself. I am Arjen Schaafsma. I'm a neurologist in the Martini Hospital in Groningen in the Netherlands. I would have loved to come to you in person and give this presentation real life, but as things are with COVID-19 and with the time difference, we have decided that this video presentation is the best alternative. What are we going to discuss today? First, I will take you with me and explore a new way to look at the blood flow velocity signal that is recorded with transcranial Doppler. But my ambition is greater. I will also ask you to reconsider the way we think about cardiovascular physiology and see whether we can look with a different view to the signals that we have, that we are so familiar with. Because I'm not present at your Congress, I'll ask you to refer with questions to the distributor of DWL, and I'm sure they can help you further. Well, let's start. My talk is in two parts. The first is what kind of innovation have we introduced for the TCD signal? But also, and that is the second part, more importantly, why have we introduced this TCD innovation? So let's go and see. We have a lifelong alliance between Neuromon and DWL with as mission to improve the transcranial Doppler functionality so that we can provide a better hemodynamic monitoring in critically ill patients on the intensive care unit. I'm sure you are familiar with transcranial Doppler. It's an ultrasound technique to record the flow velocities in the larger arteries of the circle of Willis. It has great advantages because it's non-invasive. It has you can assess the cerebral hemodynamics, and it can provide emboli detection. There are many clinical indications for transcranial Doppler. There are therapeutic indications such as the sonothrombolysis in acute ischemic stroke, but there are also many diagnostic indications like emboli detection, for instance in persistent foramen ovale or in the risk for stroke. And now with the COVID-19 we know that there are many emboli in the bloodstream, so TCD can be helpful in detecting them. We can also use transcranial Doppler for diagnostic purposes like assessing the collateral circulation in the case of carotid artery stenosis, or in the case of brain death. And we can use transcranial Doppler to assess intracranial hemodynamics, for instance on the intensive care unit, during carotid artery surgery, or in intensive care with patients who suffer from COVID-19. My talk will focus on the middle cerebral artery because this is the artery that has the largest territory in the brain, and also because there are crucial brain functions that are governed by this particular artery. Okay, if we record the flow velocity, we get the Doppler shift and of course the spectrum of the flow velocity signal, and we will concentrate on the envelope. And the envelope is the maximum flow velocity that is encountered within the vessel at any moment of time. It is of course important to have parameterisation of the transcranial Doppler signal because we want to compare one patient with normal values, or we want to compare different subjects with each other, and so it's important that we describe the signal in numerical values. It would also be very convenient if we have the numerical values and we can do a reverse calculation. This means that if we have the numerical values we can kind of reconstruct the flow velocity signal as it was. Now, since TCD was introduced in the 80s of the last century, we are stuck with very old parameters. And I'm sure you're aware that these are the typical parameters that we express the pulsatile signal with. The peak systolic flow velocity, the mean flow velocity, the end diastolic flow velocity, and often people make use of the pulsatility index, which is the difference between the peak systolic velocity and the end diastolic velocity divided by the mean velocity. But there is more in the signal, and to show this I give an example in a recording in a patient who does a deep breathing procedure. And deep breathing means that you do an inhalation for 5 seconds and an expiration for 5 seconds. And then, of course, you get fluctuations in the heart rate, but you also get fluctuations in the blood pressure and in the flow velocity signal. If we do that in a neat way and we do a bin averaging, this means that you take parts of the signal and put them and average for different in different bins, you can get an average signal and the changes of the signal in different phases of the inhalation of expiration. And this is such a recorder. Here we can see that the signal, especially the systolic part, contains of 2 peaks. The first peak, or systolic 1 peak, that is rather invariant, and the second systolic peak that varies with the respiratory phase. And this is important because we are convinced that within systole there are 2 phases that differ with respect to the physiology. And therefore, if you kind of summarize that in brief, we say systolic 1, first systolic peak, is not the same and does not have the same physiological background as the second systolic peak, or sys2. Also, the old parameters have significant drawbacks. Especially the peak systolic flow velocity and the pulsatility index, they simply take the maximum flow velocity during the heart phase. And this means that they make no difference between a first or second systolic peak. And we think this is disadvantageous. Also, the signals are angle dependent, and many of the parameters are heart rate dependent. Mean flow velocity and of course end diastolic flow velocity is really heart rate dependent, and we know the heart rate anyway, so why make the parameter dependent on it? For instance, in carotid artery stenosis, I'm sure that you are aware what this means. There is an obstruction in the feeding artery to the brain, and the problem of such an obstruction is mainly because there are thromboemboli forming and they are taken with the bloodstream into the brain and can give T-hour stroke. But there is also a hemodynamic consequence of a carotid artery stenosis. And if you take the old parameters and try to see whether you can find a difference between patients with a carotid artery stenosis, which are indicated in red dots here, and normal subjects, you can see that for the old parameters these 2 groups completely overlap. This is unsatisfactory. So we've come up in 2012 with new parameters for transcranial Doppler. We decided that it would be beneficial to make a difference between this first and second systolic peak. And we also decided that we don't want to have the end diastolic flow velocity, but we want to have a diastolic flow velocity as a fixed interval with respect to stroke onset. And when we use these parameters, we can see that we can find a clear distinction between the patients with carotid artery stenosis and the patients who don't have a stenosis. So this was very promising for the analysis of the TCD signal. We are convinced that the improved parameters presented in 2012 describe the flow velocity signal of the middle cerebral artery in more detail and thereby improve the discrimination of pathology. They improve the monitoring of the hemodynamic status, and in principle they allow the reverse calculation of the signal. So if you have defined diastolic flow velocity, you know the heart rate and you know the first and second systolic peak, then you can also redraw the middle cerebral artery flow velocity signal as it was when you recorded it. Now, how is this implemented on the DWL apparatus? Here we can see the standard screen layout with the middle cerebral artery flow velocity, and in white the envelope of the maximum flow velocity. And the software takes 10-second intervals and does an analysis on that, finding these new parameters and plotting them against time. That is the left side of the right screenshot. You can see in time different parameters along the y-axis, the diastolic flow velocity at 560, the second and first systolic peak, and on the right you can see that particular flow velocity signal and where the software finds the different peaks. So here are the dots. the first systolic peak. In this case, the first systolic peak was markedly smaller than the second systolic peak. The incisure, which is the closing of the aortic valve. The acceleration, which is the speed of change of the flow velocity signal at stroke onset. And the diastolic flow velocity at 560 milliseconds after stroke onset. The software allows you to have a cursor and go through the signal and then plot or present the signal as it was at that particular moment of time. And this is an example, for instance. This is during carotid surgery, and this is the moment that the clamp is released. There are two lines in the plots: the blue side, which is the contralateral side, and the green side, which is the ipsilateral side to the side of desobstruction or endarterectomy. And you can see exactly the large increase of the flow velocity signal and of the acceleration at the moment that the clamp is removed from the vessel. And if you hover with your cursor over the signal, you can get the plots at the bottom right and see where the dots are, where the software has found the first and second systolic peak, the incisure and the diastolic flow velocity. And so you can get more hold of the change of the signal. And we can see that before declamping there is a CIS2 dominant signal where the CIS1 is almost not visible, but after declamping there is a large increase of the whole middle cerebral artery flow velocity, and CIS1 and CIS2 are become defined again, and you can see the different peaks and see how they change over time. Another example is a study we did on our intensive care unit. This was a group of patients who was septic and received fluid challenges. And every 30 minutes a fluid challenge was given. We recorded with transcranial Doppler, we recorded the middle cerebral artery flow velocity. And also we recorded the cardiac output. And then the intensivist decided whether another gift of fluid and another fluid was necessary. And then we repeated the measure until the intensivist was satisfied that enough fluid had been given. And this is how the signal changed. So when there was a low blood pressure and the fluid the middle cerebral artery flow velocity showed as the graph at the left. And we see that there's a marked CIS1, but there is no CIS2 peak present. And during rehydration, after about 2 liters of, or 1.5 liter of colloid, we gradually see the CIS2 component returning in the signal. So we can see that the fluid challenge changes the middle cerebral artery flow velocity, and possibly we can decide whether enough fluid has been given by the fact whether the CIS2 peak has returned again or not. This paper has been published in 2017. Now this was the top of the iceberg. This was only showing what new parameters of the TCD signal can do, and how we can look better at the signal and better understand what the changes are and what needs to be corrected in the case of an intensive care patient. But more importantly, we should ask ourselves, why is this so important? Why should we make a difference between the first and the second systolic peak? And this has gradually grown during the last few years. So if we go back to our view on cardiovascular physiology, it is mainly dominated by what Harvey wrote in the 17th century. And that is that the heart is responsible for all blood flow in the body. That the arteries and veins are connected by capillaries, and that the blood is not produced at one place and resorbed at another, but that the blood constantly circulates through the body. So at that time that was revolutionary. And that was because people thought at that time that the arteries did something with the blood flow. But Harvey was very clear about this, and he literally said, do not let the thickness of the arterial tunics impose upon us and lead us to conclude that the pulsative property proceeds along them from the heart. So he excluded the possibility that the arteries contributed to the pressure wave from the heart. Now that is something we want to discuss here. because the pressure wave changes on its way through towards periphery. It is remarkable that the pulsatility increases, that the systole becomes broader, and that the maximum in the systolic phase of the signal is reached earlier. And this is strange if you think of it. Another important observation is that the speed with which the pressure wave moves along the arterial tree increases towards the periphery. So the further away you are in the arterial branching tree, on the branching of the arterial tree, the more rapid the pressure wave moves along the arteries. And that is as if there is energy added to the signal. Apart from Harvey, another important contributor to our view on cardiovascular physiology was Frank. And Frank lived in a time that they extinguished fire with a kind of fire extinguishers as modeled here. So there was water and there was a container in which the pressure was kept very high by pumping air in it, and then you could enough power to spray water into the fire. And that model was adapted for the cardiovascular system. And so Frank stated that the heart is a pump and it delivers volume to pump the blood into a large elastic artery, and there the energy is stored and only to be released over a resistance by which the blood flows into the periphery. So this is mainly the model that we have incorporated. A large volume at a certain pressure that gives you the potential energy of constant blood supply to all the tissues in the body. But we should ask ourselves, is that really true? Because the arterial system looks like this. It is continuously branching, and the cross-sectional area of the arterial system is much smaller at the start, at the aorta, than if you add all the different branches of the arterial tree together. The total cross-sectional area is much larger in the periphery. And this is demonstrated by my son, who is blowing through a funnel and trying to extinguish the candle. But there is no energy left because the energy dilutes over a large surface. And he is unable to do it like this. We have modeled that, and that's done over here. Here is a group of 7 capacitances, and we pump blood into the first capacitant, which is mainly an elastic system. So if you pump a volume into the first capacitance, then the volume can either stay there or flow over a resistance to the next. And in the next, again, the volume can stay there or flow over a resistance to the third capacitance. And then you can understand that much of the pumping energy of the heart gets lost the further away you move to the periphery. So at the end you have a low pulsatile signal. And that is not our experience, because the further we look away from the heart, the larger the pulsatility becomes. Now we know that there are smooth muscle cells in the wall of the arteries. And we also know that they are electrically coupled by gap junctions. So a depolarization of one smooth muscle cell will rapidly spread to the next and rapidly spread to the following. The orientation of the smooth muscle cells is circular. And we also know that smooth muscle cells respond to stretch. Stretch may induce a depolarization, and if the depolarization really moves electrotonically along the smooth muscle cells, you may expect that a certain contraction arises that moves along the arterial tree towards the periphery. And this is the basis of the new theory that we have developed, and that's the theory of arterial acceleration. And basically this says that in every heartbeat, at stroke onset, there is a very brief contraction of the arteries in the arterial tree, by which the pressure wave from the heart is amplified and is distributed along all the different branches. And that could really explain why the pressure wave increases in speed towards the periphery and also increases in amplitude. If you put that in a model, then we can see this low pulsatility signal that we had, but now suddenly at stroke onset we decrease the capacitance of all those 7 capacities, and then we can see that there is a first peak in the signal and that the pulsatility becomes higher at the far end, imaged here by changes in color of pink and blue, showing that there is more pulsatility in the capillaries of the arterial bed. So that is why we think it is very important to look at these 2 systolic peaks. The first systolic peak, that is the part of the arterial acceleration. It is generated by a brief contraction of the arteries in the arterial tree that moves like a peristaltic wave all along towards the periphery. And the second peak is actually the stroke volume, say the actual volume ejected into the aorta and how this spreads over the arterial tree. If we apply this new view on pulsatile signals to aging, then we come up with the following. We know for long that middle cerebral artery flow velocity decreases with age. And that was due to a study by Akkerstoff in 1990, who investigated 158 volunteers in a wide range of ages. They were all supine and breathing normally, and he found a decrease of mean middle cerebral artery flow velocity of 0.41 to 0.45 centimeters per second per year. We have done a similar study, but now we have taken these new parameters. So here are the first systolic peak, the second systolic peak, and the diastolic flow velocity at 560 milliseconds after stroke onset. And we can see that there is a decrease. The first systolic peak decreases with 0.63 centimeters per second per year, the second systolic peak at 0.46, and the diastolic flow velocity decreases with 0.38 centimeters per second per year. So the difference, the aging, the effect of aging is different for the different parameters we have now recorded. And what I was telling you about regenerating the flow velocity signal from the parameters, that is what we've done here. We have looked at what would be the average systolic 1, the average systolic 2, and the average diastolic flow velocity at 560 for a person of 20 years. And we have also looked what would be the case for a person of 80 years. And now we can see that if you're young, your middle cerebral artery flow velocity will be cis1 dominated, large cis1, and the mean flow velocity will be much higher than when you're old. If you're old, you have a low mean flow velocity, and you can see that the cis2 becomes more prominent in the signal than the cis1. So these 2 peaks vary with age, and we think that's very important. And of course, aging is a loss of elasticity that occurs, and thereby the arterial compliance decreases, vessels dilate and elongate, the pulsatility increases, the wall shear stress increases, and of course atherosclerosis is an important result of aging of vessels. You can also explain this in a bit different way, and you can say that if you're young, you have very elastic arteries, and you can store a large volume within those arteries without a large rise in pressure. Because when you're old, there is more arterial stiffness, and you only can store a small volume in the same artery at the same rise of pressure. So the elasticity of the arterial vessels decrease, and that's also effective for the new parameters that we have developed. So if you have a group of subjects and you want to study them, you have to take aging into account, and then we come up with the question how to correct for aging. Now, a way we thought about this, how to do this, is by calculating Z-scores. And Z-scores is the amount of standard deviation that a certain measure deviates from what is expected for that age. That is graphically represented here. So the thick black line is the mean. That would be the flow velocity expected at a certain age. The x-axis is the age and the y-axis is the flow velocity. And the Z-score is just how many standard deviation a certain measure deviates from that expected value for that age. And we can use these Z-scores to correct for normal aging. so that subjects can be compared inter-individually. And we can use this for physiological tests, but also for pathological states. Since if we have a patient on the ICU and we want to determine whether the flow velocity is normal or abnormal, it will make a huge difference if the patient is 20 or whether the patient is 80. And we have to correct for the age. If you do that for the first systolic peak, for the second systolic peak, and for the diastolic flow velocity at 560 milliseconds after stroke onset, and for the heart rate, you can make an ensemble of those 4 Z-scores and graph them in a radar plot. And that has been done here. And now you can see a kind of plot with the vertical axis, cis1 towards the top and the diastolic flow velocity towards the bottom, cis2 towards the left and the heart rate towards the right. And the middle black line is what would be expected for a certain age. And the outer black line is 2 standard deviation larger than expected. And the origin is 2 standard deviations smaller than expected for a certain age. And in this way we can very easily represent the middle cerebral artery flow velocity on an intuitive way. What we found in the sepsis patient, which was a rather large group, we found that remarkably all the parameters were very much higher than we would expect for normal subjects under healthy conditions. So CIS1 was more than 2 standard deviations higher than expected. CIS2 was more than 2 standard deviations higher than expected. The diastolic flow velocity was slightly less than 2 standard deviations larger than expected. And heart rate, of course, as you all know, is very high and much higher than expected for that age. And fluid resuscitation gradually restores these values to the normal. Now this is a small video presentation of showing you how you can follow these different parameters over time. This is a speed up of a patient with syncope, and you can see that if you maybe you didn't notice, but at first there was a normal heart rate, and then suddenly now we have a very low heart rate. We had a phase that there was a high heart rate and a very high systolic 1 peak, and then everything changes during syncope, and we come up with this graph, which has a large CIS2, a small CIS1, and a very large heart rate. So this is only to show you that by plotting these 4 parameters as set scores over time, we can see in what kind of condition a patient is from moment to moment. Now with this new innovation in TCD, by defining these new parameters, by defining age-corrected set scores, we are trying to make the middle cerebral artery flow velocity, the TCD signal, more better available to the intensivist, so that you have a more intuitive way of interpreting what is happening with your patient and what should be changed to get your patient in a better condition. And I think that we are a great way, or have moved a great way to really come up with such a solution that is can be applied in intensive care circumstances now. If you are an early adapter and you decide that you are going to work with these new parameters and use these set scores and using the NMA software, I think that you are serving a dual goal. First, of course, of shifting your view on the TCD signal, but also you are developing a new perspective on cardiovascular physiology and accepting the idea that not only the heart is responsible for the propagation of blood and the pressure wave over the arterial tree, but that the heart is helped by the arteries themselves, by this arterial acceleration. My presentation stopped here, but now with COVID-19, and we just finished a very small study in 9 COVID patients, I thought I'll just give this to you as well. We did a small study in 9 patients and saw what COVID-19 did with the middle cerebral artery flow velocity, and we found a very different pattern than in our sepsis patient. In the COVID-19 patient, the heart rate was usually normal, and there was a much higher increase in the first systolic peak than in the remaining parameters. And if we plot the results of our sepsis study on this plot, I hope it works, yes, there it is, then we can see this change. We can see the difference in the heart rate, and we can see that sepsis patients really differ from those with COVID-19. And hopefully this will better improve our understanding of what is happening pathophysiologically in this devastating disease. So with this I come to the end of this presentation, and I hope that you have become interested in these new parameters, have become interested in the idea that parameters of middle cerebral artery flow velocity, but also of blood pressure, of course, need to be corrected for aging, and that you have become interested in the idea of using Z-scores to correct for aging. Then, of course, the Rader plot, which makes it very accessible for intensivists, looking on one plot and seeing immediately what happens with the patient. That would be the image of the future, and hopefully implemented in many intensive cares throughout the world. So with this said, I would like to finish my presentation. I'm sorry that I am not available for questions, but I'm sure that the distributor of DWL will be helpful, and if there are questions that they can't answer, I'm sure that they will mail them to me or let me know, and I will try and respond as good as I can. Thank you very much for your attention.